Hello everyone. So in this lecture, we are going to discuss another problem from 2D elasticity uh, where the polar coordinate system will be utilized. And this is the problem of the pure bending of a curved bar. Now, as you can see in this uh, diagram, we have this uh, thick curved bar and it is subjected to this kind of pure bending moments which are externally applied. This m naught is the externally applied bending moment. The inner radius here is a, this is b. These are arcs of concentric circles, and we are supposed to find out the stress distribution here. Now, if you think about it for a moment, this problem, although uh, it does not involve full circles, it is still very much an axisymmetric problem. It is an axisymmetric problem because no matter which cut section you may take along the length of this curved bar, you will see that there is no difference in the stress distribution there. We still don't know what the stress distribution will be, but you take any cut section, the situation will be the same, because at that cut section the only uh, the only uh, uh, resistance that will show up will be a bending moment to counteract this externally applied bending moment. Okay, so uh, the most important question to ask and to get a grip of before we can proceed to the solution of this problem again in Jupyter Notebook using symbolic Python is uh, what are the boundary conditions present here. Okay, so this is our entire geometrical domain and we ask what are the boundary conditions. So just as we had done in the case of our previous problem on the pressure vessel, we can note immediately that at r equal to a and at r equal to b, we can write down the values of the sigma rr. Okay, and they are very much zero for this problem, unlike the pressure vessel where we did have an internal pressure acting at radius a and an external pressure acting at radius b. Here we do not have any such pressure, so the values of sigma rr both at r equal to a and at r equal to b, that is going to be 0. So we write that down first of all. So sigma rr equal to 0 at r equal to a, sigma rr is equal to 0 at r equal to b. Done. Next, you note that this is a situation where we do not have any force along the axis of this bar. What I mean to say is that there is no axial force here. There is no axial force here. All right. So how can we represent that? We can. So you please note that suppose you had a. Let me just use this little rough space here. Suppose we had this kind of a very familiar beam situation. Okay. Now usually we take this kind of a longitudinal axis to be our x, so that the stresses present here are like sigma xx. This is a very rough drawing, of course, so that the entire axial force for this beam would be expressed as an integration of this sigma xx over this length and through this thickness. In this case, what is the normal stress acting on this vertical face or this edge or this edge? What is the normal stress? That normal stress is nothing but sigma theta theta. So the axial force being 0, that has to be expressed in terms of the integration over sigma theta theta for the present case. So sigma theta theta here, that has to be integrated over r, considering these kinds of elemental strips of thickness dr, where we also understand that into the plane of the screen we have a width equal to 1, and this integration has to be carried out from r equal to a to r equal to b, and that result is going to be equal to 0. For the final boundary condition, I will have to write down the bending moment, and this is the most important one, because through this the externally applied load will come into the picture. For that, what do I need to do? So you please note again, for this kind of a beam, the bending moment would be written in terms of, so suppose if we have this kind of a y-axis here, the bending moment would be written as y times sigma xx dy integration from minus h to h, where twice h is the height of this beam. Correspondingly, if we consider this edge, we again have to write the bending moments in terms of this sigma theta theta again, but this time multiplied with the moment arm r. So what we write is r sigma theta theta dr times 1. So you understand that this part, sigma theta theta times dr times 1, that is the elemental force acting over a little elemental thickness of this edge. The r is the moment arm which will result in this bending moment, and we have to carry out this integration from a to b. Now this is a very important point what I'm going to discuss now. Let me just consider this edge separately here. Okay, let me just consider this edge separately, and I slightly zoom into it. What I'm doing here is basically this. I'm considering a little elemental thickness. Okay, so this thickness, this is my dr. This is my dr. Over this, I have the presence of my sigma theta theta, which is normal to that plane, and the moment is calculated using this r variable. So that is in this fashion. So if I have to take the proper sense of this moment, I have to remember the convention of the vector cross product, which actually generates these kinds of moments. So that comes out from the consideration of r cross f. Here the f is due to the sigma theta theta. So the sigma theta theta times dr times 1, where the 1 is the unit width into the plane of the screen, that is my elemental force that is in the direction of theta, and the moment arm is in the direction of r. So overall the sense of the bending moment will be in this fashion, will be clockwise. However, you note, so as written, this entire entity that has the sense clockwise, but the externally applied moment is given in an anti-clockwise fashion. So all that you have to do to capture this information is just to write this as minus of m naught. This is the most important piece of information that we write for this boundary condition. There is another condition which we can write here, which is that the shear stress along this edge, the shear force is 0, but you note that when we consider an axisymmetric problem, the area stress function is going to be independent of theta, and we have already seen in the previous video that when we have such an area stress function, the sigma r theta identically turns out to be 0. So without any further discussion on this writing app, let us go towards the actual implementation of this solution using the eddy stress function approach in the Jupyter notebook. All right. So I have fired up a new file here in Jupyter notebook, and as before, the first thing that I'm going to do is to import everything from my Polar Utilities package. So from Polar Utilities, import star. So the first few steps that I'm going to carry out here will be exactly the same as what I did in my previous file when I was trying to solve where I went on to solve the pressure vessel problem, the thick wall pressure vessel problem. And so likewise, what I'll do is I'll set up an eddy stress function which will be theta independent. It will only have a dependence on R. All right, and as before, I can find out the polar biharmonic of this file, and you see, because I have set it up to be independent of theta, there are only the terms involving the R here. And now if I have to solve the biharmonic equation, so all that I have to do, just like the previous file, I'll have to solve an equation, and that equation will be the polar biharmonic of phi equals 0. So everything to the left of this comma is the left hand side of my equation, and on the right hand side I have my 0. So basically what I'm trying to do here is set up through this equation, through this EQ, and this capital EQ command built in, that is built into symbolic Python, the polar biharmonic equation. Okay, and in this step what I'm going to do is solve this equation. So as before, as in the previous video, I am obtaining this solution, but again I would like to write down my solution in terms of capital A, B, C and D. So again, like before, I will just quickly rewrite this thing. So phi will be rewritten as A times log of R plus B times R square log of R plus C times R square plus D, and I'll display this nicely, but for that I have to first import this from this IPython. Let me just do that quickly. This is exactly like before. All right, this is what I wanted. Now with this in hand, I can actually go forward and try to implement or at least set up the boundary condition equations. Okay, so for the first boundary condition, let me just take a quick look back at my writing app. So the first condition is sigma RR is equal to 0 at R equal to A. So the first LHS, okay, for the corresponding to the first boundary condition, that will be just the substitution of the sigma RR with R as A. But you note that I have not yet actually set up my stress variable, so I need to do that first. I'll go to the boundary conditions just after that. So again, like the previous file, I invoke the sigma RR function call that is already defined within the polar utilities file. Similarly for sigma theta theta, I use it like this, and for sigma RT, I have my function called as sigma underscore RT, and I display all of this in a nice fashion. This is my sigma TT, and this I actually write as sigma theta theta, and finally I have my sigma RT. So this is sigma R theta. Let's display that. All right. As I had said just a while ago, for phi independent of theta, it will turn out that the sigma R theta is actually 0, which I had already seen in the previous video. Now, again in the previous video, we had considered the cases where the circular domain would be devoid of any hole first, and then the case where it would actually have a hole, including that r equal to 0 point, the origin. Now, if we look at our diagram, this is certainly the case where if you can just imagine for a moment that these arcs are parts of circles. So this is actually the center of that circle, and we do actually have a hole here. Okay, so this is our hole. Now, when we had discussed in our previous video that for the considerations of cases involving such holes, there can be very many different cases, and we had gone on to take the particular case of a not equal to 0 and b equal to 0. But now for this current problem of the pure bending of a curved bar, we don't have to make any such a priori assumptions. What we can do is we can keep the a, b, c unknown as they are. Let me go back to the Jupyter notebook file. These a, b, c, I will keep them unknown as they are, and instead I will just set up my boundary conditions and let the maths take care of these values. It will turn out that I can actually obtain proper values for corresponding to those boundary conditions. So first job at hand now is to set up the boundary conditions. So for the first boundary condition, sigma rr equal to 0 at r equal to a, the left hand side will be just the sigma rr expression, but where the r is substituted by a. Next, for the RHS, I just have 0. So the first equation corresponding to the first boundary condition will be LHS1 comma RHS1. That's it, and I can display this. Next, for my second boundary condition, I have similarly the sigma RR, where R will be substituted by B, and the RHS will be simply 0. And this will be my second equation. Let me look at the third boundary condition. This third boundary condition is written in terms of the sigma theta theta, and that is actually an integration from a to b. So LHS is equal to sim dot integrate sigma tt r going from a to b, and RHS. So this is going to be LHS3, and RHS3 is equal to 0. So my third equation will be set like this, and I can just display the third equation also. And finally, for my fourth equation, Uh, so for my fourth equation, let me take a quick look here. What I need to implement is this r times sigma theta theta integration from a to b, that is equal to minus m naught. Now if I come back to this Jupyter notebook, you will note that nowhere till now I have defined my m naught. Okay, so it's high time that we did that. So let's say this m0 is defined like this. So for the LHS, again I have to implement an integration. This time r times sigma tt, and the domain of integration is the same as before, r going from a to b. The RHS this time will not be 0, rather it will be minus m naught. So equation number 4 corresponding to the fourth boundary condition will be set up in this fashion, and again I can display this fourth equation as well. So let me implement this very important input cell, and let's see. Right, so I had forgotten to define these inner and outer radii A and B. So what I can do is, staying in this cell, I can press my escape key and press the letter A, so that an input cell will be incorporated just above it. It is not necessary for me to go to a new input cell, but this will be a reminder of what we demonstrated in our preliminary lectures. So we have inputted an input cell, so A comma B. So this will be symbols A comma B, and I know that they need to be positive. That's it, and this time it should work. All right, so I have four equations, and these four equations are being displayed here. Now you please note that they may look a little bit complicated, involving the log and everything, but if you just look at the unknown quantities, okay, this A, B, C, they are, so these four equations, they are very much like linear simultaneous equations involving this A, B, and C. Okay, so we have uh, uh, apparently we have ended up with uh, four equations for three unknowns, but not a problem, because symbolic Python, we know, can handle uh, this kinds of situations, as was demonstrated in an earlier video, also corresponding to the case of to that example problem of a simply supported beam under uniform loading, where we had actually supplied more equations than the number of unknown coefficients of the area stress function. So not a problem. Okay. Uh, So let's actually go ahead and try to solve this equation, this system of equations. So for that, sim.linsolve, because these are linear equations that I just mentioned. The equations are equation 1, equation 2, equation 3, equation 4, and the things that I'm going to solve for are A, B, C, and D. Well, I don't need D, so A, B, and C. All right. Now, this will be stored in this, or packaged into this solution variable. Let's just see if this thing works. So it has worked fine apparently, because no error is being displayed. So what we can do is, we can extract the solutions uh, into some variables like this. So A solution is equal to solution index 0, B solution is equal to solution index 1, and C solution is equal to solution index 2. All right, so we can display these things in a nice fashion again. quite repetitive in nature, but the end result is nice. Uh, so as you can see, these are quite long expressions. Okay. Uh, and you can also see that there are some terms where you have these kinds of dangerous looking expressions. Okay, but what symbolic Python has basically done is it has tried to shorten the length of these expressions uh, by doing some simplifications, or well, depending on your viewpoint, whether it's a simplification or a complication, it has tried to contract these terms using the properties of logarithms. Okay, but you can very well expand these things and work out uh, more simple looking expressions. But the bottom line here is that the fact of the matter is that we have ended up with solutions for A, B, and C, and all that we need to do is go back to the expressions of sigma RR, sigma, and sigma theta theta to and substitute these solutions, and we will have our answer in our hand. So let's try to do that. So sigma RR solution equal to sigma RR dot subs A comma A solution, B comma B solution, C comma C solution. And similarly for uh, sigma theta theta, and we know that sigma R theta is identical is 0. So we can again display this uh, in a nice fashion like this. So this will be theta theta. Let's see what this gives us. Oh, I had forgotten to write one command here. So you see, without the LaTeX rendering, it gives us not at all a pretty input, pretty output. Okay, so we must provide this kind of a, let me retype that, sim.latex sigma RR and sim.latex sigma ET. Let's try this once again. So I need to write this as sigma RR solution. Otherwise, it is just expressing the original unsolved expressions. So see, these are quite huge. Okay, these are quite huge expressions. Just look at that. Okay, so let's see what happens if we try to simplify these expressions. So all that you have to do is just ask SymPy to use this simplify command. Let's see if this gives us anything better. So this is somewhat better looking. Now you can see that if you were doing this by hand, then for terms like this, what you would actually do is to expand this out, maybe take the minus a square b square as a coefficient of this log term. Similarly, here you take the a square as a coefficient of this log term, and proceeding similarly with other such expansions, you can get a more familiar looking expression for this sigma RR solution and the sigma theta theta solution. Okay, but again, the more important thing to note is that this kind of tedious algebra has really been offloaded from your brain into this computer algebra system of symbolic Python. Okay, and the good thing about it is, I again emphasize that if you require perhaps numerical solutions to these, you can go ahead and make the appropriate substitutions, plot it out, and do various kinds of post-processing analysis with this. All right. So with this, I'll end this lecture, but with the understanding that this problem is not really over, because we are only stopping here currently with the solution of the stress fields, but it is very much possible to go on uh, uh, to obtaining the strain fields by considering linear elastic isotropic behavior, and then we can go on to find out the displacement fields also. So later on we'll come back to this problem, and try to find out those variables, the strain fields, and very importantly the displacement field. All right, thank you very much.